finance, economics, statistical physics, modern probability theory all rely on Brownian motion, a kind of random or stochastic process. But it's just wild, and despite being continuous, its paths have fractal properties, which are not differentiable at all, at any point. This breaks standard calculus. Techniques developed over centuries fail completely. Monstrous, a lamentable plague, an outrage against common sense. These are just some of the ways mathematicians of the past have described such functions. Allegedly, but I'll get back to that. Stick around, we'll see why Brownian motion, along with its crazy properties, is necessary. Not only that, but it's good and natural. You want to model stock prices, or particles in a fluid, any system subject to random noise, then it's invaluable. In fact, the very same properties which supposedly scared and outraged past mathematicians are Brownian motion's greatest strength, and new types of calculus enable us to handle it with ease. Welcome to Almost Sure. For millennia, mathematicians have been obsessed with smooth curves, ever since antiquity. Circles, ellipses, conic sections, triangles. Okay, those have sharp edges, but still, they've got three straight sides, so they're piecewise smooth. And polygons, polynomials, or rather, the graph of a polynomial is a smooth curve, and so on, and on. These are all differentiable, so if we zoom in at any point far enough, it looks like a straight line, whose gradient is the derivative of the function. So let's try and use this to make some money. Consider a stock whose price varies over time in some way, like this. How can we profit from trading it? Well, how about selling it for more than you bought it for? Obviously. Trading 101, buy low, sell high. Easy, done. But most day traders lose money, so it's easier said than done.
Done, Pete.
You can't know the future. At whatever price you buy, you don't know if it will go higher, or if it does go higher, you don't know by how much, so you don't know how long to hold it before selling. Well, here's an idea. Differentiate the stock price with respect to time. Whenever the derivative goes positive, buy. Whenever it goes negative, sell. That way, you hold the stock whenever the price is going up, so you're making money. And you're out of the market when it's going down, so you can't lose. Free money for everyone. But that can't be. So, what gives? Well, let's look at the charts of some actual stocks. I'll pick some here at random. This looks nothing like a smooth, differentiable function. It's all jagged, and at all different scales. So how can something like this be modelled? Enter Brownian motion. No, I'm not talking about pollen grains moving chaotically around in water, first observed by the botanist Robert Brown, but is closely related. I'm talking about mathematical Brownian motion, which is a stochastic or random process which varies continuously over time. It's also called a Wiener process after its discoverer, Norbert Wiener. As it's random, this is not just one function, but rather it's a probability distribution over all possible continuous functions. But we can simulate individual paths to see what a typical path looks like, and here we go. Well, it does look a lot like the path of a stock, right? And we can describe this mathematically as a continuous stochastic process, and its increments over consecutive equal time steps are IID, or independent identically distributed, and its distribution up to any time t is normal with zero mean and variance t. But let's look more closely at this. Let's zoom in. When we do that, well, it still looks like a Brownian motion, but it's scaled up, so it's more volatile. In fact, if we zoom in the time axis by a factor n, then this scales the variance by n, and so the standard deviation is scaled by the square root of n. So we should scale the process by the square root of n if we want it to still look like a Brownian motion. Now this doesn't preserve the aspect ratio while we're zooming, but if we do this, then it's still a Brownian motion, so there's self-similarity of the distribution. And we can zoom in at any point. We don't have to just do it at time t equals 0, so let's do this. Zoom in and keep zooming to see what Brownian motion looks like really, really close up. Okay, that's enough. This is like watching my crypto portfolio, but you get the point, so let's go back out. It's pretty wild, right? A typical path of Brownian motion has got fractal properties. However much we zoom in, it's still got lots of detail, which never ever goes away at any scale. But it also never exactly repeats itself. It certainly does not converge to a straight line or anything like that, so it's far from being differentiable, and you can prove mathematically that it's not differentiable at any point, almost surely. Now if we try to trade a stock price which follows a Brownian motion, then we're in trouble, right? It's impossible to know if it's increasing or decreasing. In fact, over any period over which it increases, there's going to be subintervals on which it decreases. And those subintervals themselves contain subintervals where it increases, and so on. And if you've tried trading, then that might sound familiar. So the guaranteed winning strategy of buying while it's increasing, strictly speaking, that's impossible. Actually, you wouldn't exactly use a Brownian motion to model a stock price because it can go negative. Better to use the exponential of a Brownian motion with a scaling factor and a drift term, which is the Black-Scholes model. Anyway, people used to believe that every continuous function is differentiable, at least at most places. Sure, functions like the absolute value of x, this is not differentiable when x is 0, but 0 is just 1 point, and it is differentiable everywhere else. The first published example of a continuous function which is not differentiable anywhere was in 1872 by Weierstrass, and it looks like this. Now this is an actual deterministic function, not random, but you can see how it looks a bit like a Brownian motion path, and it does have similar fractal properties. At the time, when this was published, it was considered pathological, just a very nasty example showing how our assumptions can break down, not something that's actually useful. In fact, people hated it. Here's Charles Hermite. I turn away with fear and horror from the lamentable plague of continuous functions which do not have derivatives. And Henri Poincaré, he called Weierstrass's work monstrous and an outrage against common sense. Well, that's the story that's commonly told, and that's what I was going to tell you. It's what Wikipedia claimed, and Quantum magazine and other places. But checking primary sources, actually that's not quite right. They're either quotes taken out of context or even outright false. Poincaré did not say it was an outrage against common sense. All he did say was that people a century before him would have regarded such a function in this way. And then he went on to be pretty positive about Weierstrass's work. And Hermite, he made his lamentable plague comment in a letter to Stieltjes, in passing, before talking about some other stuff. Possibly just a kind of wordy way to say that he's got nothing more to say about these non-differentiable functions. Let's talk about this other thing that he did have a lot to say about. However, some years later, Poincaré did describe continuous functions without derivatives as monsters, and this time he seems less happy, saying that all we will ever get from such functions is to undermine the work of our ancestors. Nothing else. However, this too doesn't seem quite so negative when it's viewed in context. The term monsters, for one thing, That's not necessarily negative, it just means something big or complex. And it's talking about teaching mathematics to students. You wouldn't go all in teaching students the most general case right from the get-go, where you can't even use standard calculus. And also you shouldn't lose sight of the reasons for considering continuous functions in the first place by starting with the most general situation. So although people were not quite as disdainful or scared of non-differentiable functions as they are popularly considered to have been, they were considered examples showing how wild continuous functions can be that are not actually useful for practical purposes. So it's interesting that now, through Brownian motion, such monsters are incredibly useful and important in many ways. And in my opinion, they're beautiful. It's not just having no derivative that makes processes like Brownian motion break millennia of maths. There's various things. The familiar smooth functions that we deal with in school, these tend to be increasing or decreasing, or at the very least you can split them into ranges on which they are increasing or decreasing. And there's a discrete set of local minima and maxima, and not so with Brownian motion. Inside any interval, you can always find places where it increases and where it decreases. And it's got infinitely many local minima and infinitely many local maxima between any two times. And it's got infinite variation on any interval. So if you add up all the little increments and decrements at finer and finer resolutions, this goes to infinity. And Brownian motion never just passes through a level like a nice function would. Instead, when it crosses a level, it hits it uncountably many times. The set of times where it hits a value, let's say 0, this is random, but with probability 1, it's what's called a Cantor set. That means it's closed, it contains no intervals and no isolated points. And you may be familiar with these sets, they have fractal properties. And you may have heard how things like coastlines, other things in nature, and fractals have a dimension which is not an integer. Well, the same is true of Brownian motion. Whereas smooth curves always have dimension 1, not a surprise, just like the real line does. The path of Brownian motion, this has dimension 3/2. And I just mentioned where it crosses a level, it actually crosses it infinitely often. In fact, we can show that the set of times at which it equals any fixed value, this has dimension 1/2. And if we consider the path of a two-dimensional Brownian motion in the plane, that's a path whose x and y values are independent Brownian motion, this has dimension 2, the same as the plane itself. Even though it does not fill the space, and it in fact misses almost all points of the plane, it still manages to have dimension 2. Okay, I think that's enough counterintuitive properties of Brownian motion for now. You might be thinking we should just avoid these things like the plague, just like Hermite and Poincare were alleged to do. But no, Brownian motion is not only extremely useful, it's really necessary for a lot of cool stuff, and there's techniques to handle it. So let's move on to that. All the seemingly paradoxical or pathological properties of Brownian motion that we just saw, they're needed, and we can't avoid it, and neither should we try to. Let's look at the hypothetical case of trading a stock which has a smooth price again. We already saw that if we can differentiate it, then we can make money simply by buying whenever the derivative is positive and selling when it isn't, but we don't even have to compute the derivative. Consider any function f, which we'll take to be smooth, so it has a derivative f prime, and apply this to the stock price. The derivative of this with respect to time is f prime of s times ds by dt. That's just the chain rule. And this is the rate at which our portfolio would change value if we hold quantity f prime of s of the stock. So integrating back out, the change of f of s up to time t, this is f of s of t minus f of s of 0. This equals the profit from continuously trading to hold f prime of s quantity at all times. But this is weird, right? F is whatever we want as long as it's smooth, and our portfolio value is supposed to exactly track this function of the spot. I mean, choose F to be minimum at S of 0 and really high at other values. Then our trading strategy can only profit, and it's never going to lose. Let's try a specific example. Take F to be quadratic. So F of S is equal to S minus S of 0 squared. Then the strategy of continuously trading to hold quantity 2 times S of t minus S of 0 of the stock at time t. This should give us a profit of S of t minus S of 0 squared. And this strategy doesn't even involve the derivative of S, but we're still guaranteed to not lose. Let's try with some actual Brownian motion sample paths for the stock and use this strategy. We can simulate and see what our profit actually looks like over time. So let's do this. Let's simulate and plot the results. I'll subtract the initial value from the stock price, so we can say it starts from 0 and the stock price can go negative. That's just for convenience, so we don't have lots of S of zeros floating around. It can go negative. We can lose money, surprise! The reason our formula doesn't work? Well, even though we don't actually compute the derivative for our trading strategy, it does require differentiability for the proof to work. In fact, over each tiny interval from time t to t plus dt, I considered holding amount 2 times s of t of the stock. But what happens if we hold 2 times s of t plus dt instead? That requires looking forwards in time a little bit, so it's not an actual strategy we could use, but we can simulate it and let's see what happens. Now it is always positive. In fact, it's even greater than the theoretical value of s of t squared. But let's take the average of these two strategies. So this means we hold the average of 2 times the stock values at the start and end of each tiny dt interval. It does give the theoretical amount. So why is it like this? I mean, we know that we can't make money for free, but why does it look like this in particular? Actually, it's not difficult to show. Our profit over a small dt interval is the quantity of stock held multiplied by the change in price. And if we hold the average of 2 times the stock price at the start and end of the interval, then we get the product of s of t plus dt plus s of t times by the difference of s of t plus dt and s of t, which comes to the difference of the squares. Okay, so if we add up all these profits on all time increments, all these differences of the squares, then the cross terms all cancel out and we get s of t squared. So in that case, we do get the theoretical value as we saw from the simulation. That's good. Okay, but suppose that over the little dt interval we hold 2 times s of t of the stock, its price at the start, which in reality we must do, right? As we can't see what the future value will be, even a small time dt in the future. Then our profit on the interval, this is 2 times s of t multiplied by s of t plus dt minus s of t. Now let's approximate this by s of t plus dt, which we know gives s of t squared for the profit, and then add on a correction term to keep the formula correct, like this. And this second correction term, let's rearrange it a little bit. It comes to minus s of t plus dt minus s of t squared. So that's always negative. And then adding all these negative terms gives a decreasing process. So our profit at the end will be s of t squared minus this increasing process. But this process is the sum of the squares of the increments of s, is called the quadratic variation. And for smooth processes or smooth functions, the quadratic variation goes to 0 as your dt increments tend to 0. But not for Brownian motion. In fact, for Brownian motion, it will tend to t. So the profit from our strategy is s of t squared minus t, which can be positive or negative. Now everything is sliding into place. Remember the definition of Brownian motion. S of t is normal with variance t. So when we compute the expected value of our profit, we get 0, which it must be over any small time step. Brownian motion can increase or it can decrease with 0 mean, so any strategy will have 0 mean over each small dt step. And adding together all these, the total, the net profit, it must still have 0 mean. So this all works out nicely. We have this entirely new concept, quadratic variation, which is always 0 for smooth or differentiable functions, but it's non-zero for Brownian motion, and it's exactly what we need for everything to make sense. I'll just mention one thing I've been avoiding here, transaction costs. In real life, there's a cost to each trade, which would eat into the profits of any strategy. So maybe stock prices could still be smooth. I'm not saying they are, but they could be. But as long as the trading costs are small relative to the scale we are viewing into that, then at such resolution, the price should approximate something like a Brownian motion style path. Now here's another way to try and make money by trading a stock. And this one is not even going to involve assuming the stock price is differentiable. Let's suppose the initial stock price has a value k. And try the following strategy. Whenever the stock price goes above k, we buy and hold 1 unit of stock. And whenever it drops below, sell. So then we hold no stock. Then if the price rises above k to some level s of t, we will have held from k all the way up to s of t, giving a profit of s of t minus k. But if it drops back down towards k, then we sell. And yeah, we lose our profits, but we break even. And if it goes even further down, we're out of the market, so we've got 0 profit. In any case, we're going to have a profit of s of t minus k whenever this is positive, and when it's negative, we have 0, so we never actually lose. Risk-free gains again. We might want risk-free gains, and we might want a model which tells us how to get risk-free gains, but that's not the real world. Let's look a little bit closer. If we trade at discrete times dt apart, then when the stock goes above k, there will be a small delay up to a time of dt when we actually buy. So we actually end up buying the stock slightly above k and paying a little bit more. And then when the stock drops below k, we sell a little bit after again. So we sell for a little bit less, losing a bit of money again. This is called slippage. We're trying to buy at some target price k, but we're actually buying above and we're selling below, and this eats into the profit. And maybe it ends up causing a loss. Okay, you might say, make dt even smaller, so we're trading even faster. And this will reduce the slippage for each trade, which it will do. For each trade we're going to lose less money if dt is smaller, because we're assuming continuous stock prices. So in the limit of continuous trading, we're back to having risk-free gains, right? Wrong. Not so fast. There's one thing that can still go wrong. Even if there is less loss per trade, with very high frequency trading, there could be more trades. If the stock goes through K and we buy, so there's a tiny amount of slippage, but then it drops below it again, rises above it, and on a very small time scale, it just keeps crossing the level K, then we might have less slippage per trade, but we have more trades. So it could still add up to something significant. And remember when I mentioned one of the strange properties of Brownian motion, that if it crosses a level, it crosses it infinitely often on small timescales, and the times at which it equals some level k is a Cantor set, uncountable with no isolated points. And you might have thought this was just some pathological behaviour which has no real life meaning, but it's exactly what is necessary to take away the possibility of having risk-free gains. And yes, we must take away the possibility of having risk-free gains. And all these losses due to slippage mean that we must subtract this increasing process from our profit. And this process from the slippage in a continuous time limit, it has a name. It's called the local time of S at level K, and has an expected value which is just right to cancel out the profits, to give 0 expected net profit again. By the way, this supposed profit of S of t minus k floored at 0 that we aimed for, This is a payoff that you may recognize. It's exactly the same as the payoff of a call option on the stock with strike price K. So the local time stops us from being able to synthetically replicate a call option at zero cost, as it must do. Call options have a positive value. And if you've heard about Black-Scholes, that gives a more correct way of hedging or replicating an option, which requires that you start from a positive value, the option premium or price. And it's exactly what's needed to compensate for the trading losses in trying to replicate the value. Let's move on from trading in stocks and look at other ways in which Brownian motion is used. For example, noise in a physical system. Now consider pollen grains in a fluid being battered and knocked about by continuous random bombardment by the fluid molecules. Now this is the classical physical Brownian motion that was studied by the botanist Robert Brown. And it's quite an easy experiment to do yourself. Here's a video I took of milk particles in water just using a cheap child's microscope like this. Nothing fancy. And we can't say exactly what the effect of the bombardment by these molecules is because we can't know the positions and velocities of all the molecules in the fluid. I mean, that's impossible. And in any case, it's much too huge a number for exact calculations. But we can say statistically what's going on. The individual molecules are tiny, so individually they're negligible. But combined, they will effectively continuously impart momentum on the pollen grain or milk particle. And the net momentum transferred over any two distinct time intervals, they must be independent, effectively. And the whole thing is symmetric, so the mean must be symmetric, it must have zero mean. And this is already enough to say that the momentum of the pollen grain will be like a mathematical Brownian motion. As we discussed, its direction over each successive small interval or its change in velocity is going to be independent of all the other intervals. So it can never conspire for the momentum to move in any consistent direction, so it won't be differentiable. At least to the level of approximation where individual molecule strikes occur too fast to see. Now, mathematical Brownian motion, we see it's a good model for the momentum of these particles, rather than using it for the position. But we should really also add in some drag to stop the momentum getting too high, but still it seems like a good model. And in fact, Brownian motion is often used for the position as well as its momentum. But it still seems to work pretty well, just not quite as good, since individual pollen grains or milk particles will have a velocity. The position can't be non-differentiable. Anyway, we see that mathematical Brownian motion crops up in various places, and its supposed weird properties like not being differentiable, that's exactly what we need for reasonable behaviour of our models. I have to head out in a moment, but before leaving you, let me mention something else. You might have heard of something called fractional Brownian motion. Standard Brownian motion is a stochastic process whose values are jointly normal, and such that the increment across a time interval of width delta t has zero mean and standard deviation equal to the square root of delta t. But we can generalise. What about a jointly normal process whose increments have standard deviation some other power of delta t? Say delta t to the power of h, where h is some parameter. Then you get fractional Brownian motion, and h is known as the Hurst parameter, and it must be between 0 and 1, otherwise it just doesn't work. You get negative variances and probabilities coming in. But for h between 0 and 1 it does work, and here's a plot to demonstrate a sample path. Now with h equal to 1/2, this is just standard Brownian motion, but as we increase h, it makes it appear a bit smoother, until we approach 1, in which case it just becomes a straight line. And for smaller values of h below 1/2, we get even rougher paths than we had with Brownian motion. Now these are badly behaved, they're nowhere differentiable whenever h is less than 1, just like Brownian motion. And they'll have infinite variation over each interval. And fractal dimension is 2 minus h. Let's consider numerically computing an integral. Let's say the integral of 2b with respect to b. This is what we did before. We got b squared minus the quadratic variation. Now, fractional Brownian motion is quadratic variation with Hurst parameters less than a half. It's infinite. So this integral blows up to minus infinity. Now, this is pretty bad. But let's look at h greater than 1/2. Then, fractional Brownian motion, it looks smoother. It still isn't smooth, and it has infinite variation. It's got nowhere differentiable paths. But it does have 0 quadratic variation, and if we evaluate this integral, we get b squared. Same as with a smooth path, which is pretty nice. But even for h greater than a half, don't be fooled by the slightly smoother paths and the fact this integral worked. We still run into trouble pretty quickly. Suppose that we used b for the price of a stock, and we split time into small dt intervals. And then at the start of each tiny interval, we buy the stock if it went up on the previous interval, and sell if it went down. Well, actually, for h greater than a half, the correlation between successive dB terms is actually positive. So this strategy works. We buy most of the time when it goes up, and then we sell most of the time when it goes down. And our profits blow up to infinity as our dt step becomes small. It's just as h equals a half that we get the nice bounded integrals, and Ito calculus all works out. So Brownian motion is just right for many applications. It's not too wild to handle, it's not too smooth to be predictable, it's in a Goldilocks zone, nicely tamed by Ito calculus, giving a very successful theory of stochastic differential equations. Anyway, that's all from me. Please like and subscribe. I'm going to go away and make more videos, but don't worry, they won't be monstrous outrages against common sense. Almost surely. Oh, yeah.